Hi, everyone. Thanks for joining the webinar today. My name is Lauren Ballatin, and I work with the National Integrated Heat Health Information System based out of NOAA's Climate Program Office. Today's webinar is going to be showcasing projects supported and funded by a variety of teams across our Climate Program Office, which our moderator, Adam, will tell you more about. The presenters will be discussing research that has advanced our understanding of the compounding and cascading impacts of extreme heat, including drought, air quality, and wildfires. Registration is already open for our next webinar on May 21st. We're going to have another great lineup of speakers discussing projects that will be advancing actionable solutions to heat in urban environments. So you can scan the QR code if you're interested in registering for that. And do stay tuned also to our Climate Program Office website for updates on the rest of the series. Before we get started, I just want to add that we will have time for questions immediately following each speaker's presentation. So feel free to put those in the Q&A box as you're listening, and feel free to also add your name and your affiliation when submitting questions if you feel comfortable. So now I will go ahead and turn it over to my colleague, Adam Lang, to introduce our first speaker.
Thanks, Lauren. I am Adam Lang. I'm with NOAA's National Integrated Drought Information System. Our first speaker today is Ronald Leeper with a presentation on Do Droughts Worsen Heat Waves? Ronald Leeper is a research scholar and applied scientist at North Carolina State University and NOAA's National Centers for Environmental Information through the Cooperative Institute for Satellite Earth System Studies. He's also pursuing his PhD in atmospheric science at North Carolina State University's Marine, Earth, and Atmospheric Science Department. Leeper's research focuses on hydrological extremes and their societal impacts. The research that Ronnie's presenting was supported by NOAA's National Integrated Drought Information System, NIDIS, which sits in NOAA's Climate Program Office. NIDIS was authorized by Congress in 2006, and we're celebrating our 20th anniversary this year. And we were reauthorized in 2014 and 2019 with an interagency mandate to coordinate and integrate drought research, building upon existing federal, tribal, state, and local partnerships in supporting and creating a national drought early warning information system. Take it away, Ronnie.
Hi, Ronnie. Can you make sure you unmute, please?
Sorry about that. Okay. Alrighty. So I want to thank the authors who supported this effort. It took a village, and I just happen to be the one that gets to talk about it with you guys today. I led with this leading question: do droughts worsen heat waves? And that's primarily hoping. I think you guys know the answer to that, but I really hope what you get out of this talk is that where we're confident that it is, and maybe where some additional work could come in and kind of help back that out a little bit further. So compounding hazards, if you're new to this topic, or if this is your first time you've heard about it, the idea here is that you have two natural occurring hazards, and when they co-occur, their impacts on society superimpose or compound, meaning they're more impactful when they happen together in time than if they were to happen separated in time. We're going to be talking about heat waves, and there's a lot of work done talking about the impacts heat waves have on human health. Anywhere from heat stress. There's all sorts of populations that are more sensitive to heat wave, older folks who work outside, but also pregnant folks who can deal with preeclampsia. Heat waves also impact crop yields, so there's an obvious economic impact there. And then those who are managing farms, sometimes we don't think about it, but heat waves and those economic losses can lead to stressors and impacts on livelihoods and mental health. So those are some of the nexus and ways in which heat waves are detrimental to society. Droughts come in and can worsen this impact by reducing the amount of water available at the surface. So you reduce soil moisture, you reduce water in the streams, and so this can lead to reductions in evaporation. So more of the incoming solar energy is used to warm the atmosphere, and so it can provide an enhancement. Kind of the key three aspects of heat waves we're going to focus on in this study was how droughts modulate heat wave intensity, duration, and exposure. So there's a little bit of background there. We're going to be focusing on data from the U.S. Climate Reference Network. If you're unfamiliar with that, it's an amazing network. I got a map here showing you where these stations are located. We're going to be focusing on data from the lower 48 and the CONUS here, but we do have they do have stations in Alaska and Hawaii. There's a map here or an image showing you what a typical station looks like. High quality data, sub-hourly information. There's also soil moisture observations you can't see here, and that'll come in. That'll be important later on. You'll see, and then. For our study, we're focusing on air temperature, although the network does observe humidity, so we did compute heat index. But given the time constraints on the talk, I'm not going to really dig into that in this particular talk. Because air temperature can vary quite a bit with latitude and east to west across the United States, we're going to be deriving standardized anomalies and exploring heat from that perspective. So to kind of give you a methodological overview, it's a pretty straightforward kind of analysis. We're defining heat waves at CRN stations. If they co-occur in time with a drought, that's a compound event. So that's the term I'll be using throughout the rest of the presentation. If a heat wave occurs outside of a drought, that's what I'm calling non-compound heat waves or non-compound events. And basically, we're going to compare duration and heat wave intensity and heat exposure between compound and non-compound heat waves. To talk about the exposure, this is kind of an interesting term, and it's very similar to growing degree days or heating or cooling degree hours, if you're familiar with those. Anytime the temperature reaches or exceeds the 90th percentile, we compute the difference to see how far you're above that extreme heat threshold, and then we can accumulate that over time in degrees Celsius, and you can accumulate this over a day or over a heat wave like we're going to do in this study. This is published work, so I got a reference there at the bottom for folks who want to try and take a deeper dive, maybe look at some of the heat index that we're not going to talk about. So heat waves were defined in this project using the daily maximum percentiles. We only considered heat waves from May to September, and when we did this study, we did it 2010 to 2022. Heat waves are defined based on 3 days in a row exceeding the 90th, beginning that first day of that 3 set, and it continues onward until you have at least 3 days below the 90th in a row, and that's when a heat wave terminates. To capture a drought, we're going to be using data from the U.S. Drought Monitor. The USDM, if you're unfamiliar with that, it's a product that's produced weekly. It uses a convergence of evidence approach, so it is not an empirical indicator. They're taking data from meteorological drought, agricultural drought. They're talking to folks in the field, and they're pulling all this information together to define drought into one of these categories you're seeing here on the y-axis. We have none drought up to D4, D4 being the maximum. And in this categorical space, drought typically begins at D1. So in our analysis, we're going to be using the first week you hit D1, that's when drought begins, and it's going to end the last week you're at D1, followed by 3 weeks of no drought. And this is the same definition we use in another publication looking at the climatology of drought across the United States. Okay, so now that we've got our definition for heat waves and compound, non-compound events, we can kind of dive into some of the results here. So for the heat wave duration, on the left here, I'm showing non-compound events. So this is kind of my typical setup for my graphics. I'm always going to show just the heat wave outside of drought results. For most of the United States or most of the CRN stations, the typical heat wave length is about 4 to 5 days. You do see slightly higher averages in the southeast. And then, of course, those 3 stations in New Mexico, interestingly enough, the only 3 that have an average greater than 6. And then on the right, I'm showing you compound minus non-compound results. And so this way you're not trying to eyeball differences. When we compute the difference, it's compound minus non-compound. So positive values imply that the compounding event is greater, and negative values indicate that the compounding event is less. In this case, across the United States, a majority of stations saw an increase in the mean duration of heat waves. So when you introduce drought to a heat wave, it typically lasts longer, anywhere from 12 hours to 2 days more. And to put that in the scheme of things, The 21% of stations that see a 2-day or greater increase is roughly 1.5 times longer compared to your typical drought. And, that's a pretty big increase in time. And as you'll see, heat exposure. The other thing we looked at was heat wave intensity. And this one actually was a little more challenging to pin down. And I don't know if we covered it the best way possible, but we looked at it from two perspectives. In this first perspective, we took the daily maximum average of every day within a heat wave, and we averaged that across all the heat waves detected at each station. So on the left, top left, I'm showing you the maximum anomaly. And if you look at the scale here, a majority of stations see about a 2 standard deviation or greater increase are above normal temperatures. And even though our definition said you had to hit the 90th to put 2 standard deviations in perspective, that's the 95th percentile. 3 standard deviations is at the 99th. And so even before we introduce drought, you're already having really, really hot heat wave conditions, and just using this metric of daily maximum. If we compute the difference, the compound minus non-compound, we definitely see more stations detecting higher daily maxima. Although if you look at the difference, these are quite small anomalous changes from 0.15 to 0.3 standard deviations. They're small because it's already large before we introduce heat waves. So it's really hard to get much hotter than the 95th and certainly the 99th percentile. But in general, you see an overall pattern across the U.S. with increases where droughts increase the intensity of the daily maxima. We did this another way as well. We looked at every hour of the day throughout a heat wave, and that's what we're showing on the bottom. And when you do that, you see an interesting difference from the daily maxima. Most stations have little to no change, although a majority of them have some increase. We do have a set of stations, these green stations, where you see the compounding result in lower hourly temperature anomalies. Where we see a spatial pattern, we see in the Intermountain West, in the desert Southwest, and parts of Texas, where there's still a warmer condition when you do the anomaly average. So we want to dig into that a little bit, but before I get into that, we're going to talk about exposure to heat, which I think is a better measure than the intensity overall. So with extreme heat degree hours, if you recall, this is where we're taking the 90th percentile for every hour of the day, and throughout a heat wave, we're accumulating how many degrees we're above the 90th. So on the left, I have extreme heat degree hours for just the regular heat waves. And on the right, I'm showing the difference. And you can see there's about about 75% of the network shows an enhancement or greater degrees above the 90th. So even though when we do an hourly average over the entire event, we get most stations showing little to no change. When you're above the 90th and you have a heat wave, the extreme is much higher. And that's kind of one of the interesting takeaways between this and looking at intensity alone. So droughts definitely increase the exposure to extreme heat. Although I think some research probably could be done to understand, well, when you have more than 50 degrees Celsius above the 90th, like what type of impacts would you expect to see? I think that's something that could happen later. So to kind of look at the intensity a little bit more and understand that, Intermountain West and Southwest anomalous difference compared to the rest of the U.S., we divided the United States into an eastern and western half. And for every hour of the day, we computed the mean temperature anomaly for non-compound in orange, compound in red. And these are some really interesting results. In the eastern half of the United States, when you have a drought and a heat wave at the same time, you have a cooler minimum temperature around sunrise, 6 a.m., and you have a warmer maximum. But where you see the largest difference between compound and non-compound heat waves is not the daily maximum, it's the afternoon following the daily maximum. And in fact, you see hotter, sustained, warmer conditions under compound events throughout the afternoon and into the evening hours. It's not about until 9 p.m. where you see compound events move in line with non-compound heat waves. In the Western United States, this one took us a minute to kind of disentangle. But the key thing here is that in the middle part of the day, in the West, for whatever reason, there's really no difference in the daily maximum of temperature anomalies when you have compound versus non-compound heat waves. And then during the evening hours, the compound events are warmer, which is probably not what you would expect, considering what we saw in the eastern United States. To back up a little bit, you're cooler in the morning hours during compound events because your humidity is reduced, and humidity is a very potent greenhouse gas. So for the non-compound heat waves that have more humidity, that means as the Earth cools from long wave radiation, the humidity is going to block that heat and keep it localized at the surface. And that allows it to be a little bit warmer. We're not seeing that in the Western United States. And I think what's happening here is that drought, defined by the U.S. Drought Monitor in the western half of the United States, is primarily focused on hydrological drought. So this is how much water do you have in your stream or reservoir. So you can still have a rain event happen within a hydrological drought. It may be sufficient enough to impact the heat wave, but not sufficient enough to end a hydrological drought. In other words, recover streamflow levels. And so I think in the Western United States, we're mixing agricultural droughts with that are, wet and not wet. And so to dig into that a little bit more, we use the soil moisture data from the CRN station. So again, another shout out to CRN. We would not be able to do this without another network. So we took the soil moisture observations in this analysis, and we instead of breaking it down between drought and non-drought, we broke it down by soil moisture regimes. So we have a wet regime in the green line, a normal regime in the orange, and then the red line is showing a dry regime. So the dry regime is what I'm going to focus on here. But when your soils are dry, so this is negative 0.5 standard deviations or drier than normal, you see the pattern we saw with the drought, the compound events. It's cooler in the morning, hotter in the day, and the heat that you experience extends throughout the afternoon and into the evening hours. When your soils are wetter, yes, you are wet. You stay warmer in the day, but you do not get as hot. And so that's kind of an interesting pattern we didn't quite see as well defined when using Drought Monitor to define drought. In the Western United States, we now see that yes, when you have dry conditions in the soil, your temperatures are cooler in the morning, but we still see no, change in the intensity of the heat on average across the Western United States based on soil moisture condition. And I would say this would also apply to drought. It probably suggests we should break that region up even further. Desert Southwest is probably a lot different than the Intermountain West, and both of those regions are probably a lot different than the coastal zone from Washington through California. In this slide, we're showing you the fraction of extreme heat degree hours, and really what I want to talk about here is that a greater proportion of the variance is explained by using soil moisture conditions, dry, normal versus wet, than if we just use compound, non-compound drought based on the drought monitor. So that's kind of one of those interesting things we saw. And so I'm going to try and wrap it up here. The main takeaway that you get from this analysis that we're pretty confident in how compound events interact is that droughts increase the duration of heat waves. We saw an increase of about 1.5 at the maximum end. Again, that's an average. And because of the increase in duration, we're seeing more exposure to extreme heat. And that exposure is not really explained by increases in intensity. It has more to do with the increasing of the duration of the heat wave. Our analysis of intensity was complicated. It varied a lot. Our choice of how we measured it, daily maximum versus hourly, completely gave us completely different results. One of the key takeaways we learned with the drought monitor and that Eastern versus Western analysis is that not all droughts are the same. And I think this is an area where we really could drill down and maybe try to focus on a little bit more. Some droughts are going to be more impactful on heat waves and generate more of a compounding effect than others. And we kind of need to tease that out, which type of droughts they are. We ran into complications with the drought monitor, but I think you would see a very similar pattern even if you used an indicator like SPEI or EDDI that are tuned toward agricultural drought. And that's because when the heat wave occurs within the drought pattern, can also dictate how intense that heat wave might be. And I think regardless of what indicator you use, you're going to see an eastern versus western pattern that may be complicated. One of the other takeaways is that your exposure to extreme heat due to compounding is mainly in the afternoon. It's not necessarily daily maxima. So if your study focuses primarily on daily maxima, you're going to be missing some of that exposure that you might be getting from extreme heat that's occurring in the afternoon after the maximum. And I think soil moisture conditions, I embolded this here because I think it's important. Using soil moisture conditions could probably help us get a better understanding on the types of droughts that are going to be more impactful on heat waves. So with that, I yield back. I go to my question slide here. Thanks for your attention. Hopefully you've found something interesting out of that conversation. This is an AI generated image. I just gave ChatGPT U.S. Climate Reference Network compound heat waves. You get Smokey Bear there at the bottom. But anyways, this is my contact information, a link to the DOI, and happy to hear any questions folks may have. Thank you.
Thanks, Ronnie, for that great presentation and definitely a timely study right now. We have time for a question or two. One question that came in is, have you seen in your study, did you see any differences in soil types in drought and their impact on heat waves?
That's a good question. So we attempted to account for soil type by using standardized anomalies in soil moisture. So each station has, within its own range of variability due to soil type, a mean and a standard deviation. So we didn't specifically look at that. Although I will say a majority of CRN stations are located over sandy soils for whatever reason. I don't think that's intentional, but it just kind of worked out that way. So, if that has any bearing on some of the soil analysis, that could be something. Maybe a network that maybe has a more sandy loam kind of rich network could be used to compare. But I don't know the answer to that. We didn't really explore that.
Okay.
Mhm.
And we just had one other question come in.
Okay.
Did you stratify by urban, non-urban areas?
So where CRN stations are located, they're intentionally located away from urban areas. So they're well sited. So they tend to be in grassland areas. So we are probably sampling grassland regions more so. So there is generally no urban impact on these stations.
Okay.
Mhm.
We have a couple other questions, but we're going to have to move on, but we will work to get answers to all the questions that are coming in. So we are going to go to our next speaker. Make sure we get that up. All right. Our next speaker is Mitchell Rogers, who will present on the impacts of warming, humid summers on urban organic aerosol production. Mitchell Rogers is a PhD candidate in chemical and environmental engineering at Yale University and a National Science Foundation graduate research fellow. He works with Professor Drew Genter to study the impacts of evolving emissions, climate, and atmospheric chemistry on air quality. The work in this presentation was supported by the Atmospheric Chemistry, Carbon Cycle and Climate AC4 program in NOAA's Climate Program Office. The AC4 program investigates the chemical processes governing the Earth's atmosphere. AC4 plays a critical role in bridging the gap between process-level understanding and predictive modeling, specifically focusing on the intersection of air quality, the carbon cycle, and urban atmosphere, with the goal of informing atmospheric management strategies and improving long-term climate projections. All right, we're ready for you, Mitch.
Can everyone hear me okay right now?
Yes, we can hear you.
Okay, I think my internet connection is a little tricky, so if for some reason folks can't, please let me know and I can adjust. Maybe it's good to come back to me, but I'll try going right now. I've had some trouble sharing my screen here, so I apologize. Maybe it'd be good to go on to someone else. I'm going to try and find a better internet connection.
Yep, no problem.
Yep, that works.
Okay, so we will move forward. So our next speaker is Kristen Vandermolen, who will present on household health adaptation to compound events, extreme heat, and wildfire smoke. Kristen is an assistant research professor at the Desert Research Institute in Reno, Nevada, and a member of the California-Nevada Applications Program, the West RISA team. She has a background in environmental anthropology and conducts research on hazard risk communication and protective action decision-making, including related to extreme heat and wildfire smoke. Her work is focused in Nevada and California. The work that Kristen will be presenting on, it was supported by the Regional Integrated Sciences and Assessments RISA program within NOAA's Climate Program Office, Climate and Societal Interactions Division. The RISA program expands regional capacity to adapt to environmental hazards, supports sustained collaborative relationships that helps communities facing weather and climate hazards like flooding, extreme heat, and wildfires. Funded through 5-year cooperative agreements with NOAA, place-based and interdisciplinary teams work together to plan for and adjust to change using science and local knowledge. All right, Kristen, we are ready for you.
Okay. All right. I assume this is visible to everyone, but if not, please be sure to let me know.
It looks good.
Okay, great. All right, well, thank you, and I appreciate the opportunity to participate in this webinar. As mentioned, I will be talking about some work focused on the topic of household health adaptation to compound events, specifically extreme heat and wildfire smoke. This is very much collaborative in nature and additionally involves a DRI colleague, Yongkwan San, as well as Salim Garcia and Harley Pollard, who are both graduate students at the University of Nevada, Reno, and hold positions here at DRI. So to first give you a little bit of the background on the project as well as Washoe County before moving into some of the details, the long-term goal of this work is to identify opportunities to support household health adaptation to compound events. The near-term goal that we're working on currently is to understand household health impacts from exposure to compound events. The idea being that first we need to understand households are impacted and what their abilities are to respond to compound events in order to then eventually understand best ways to support them. And key to this work is DRI's partnership with Northern Nevada Public Health, or NNPH, specifically their Air Quality Management Division and Health Equity Committee. NNPH is a regional public health organization and the local public health authority within Washoe County. And so their partnership on this project is critical, both in terms of facilitating certain components of the research, but also because NNPH is ultimately the end user of the results. Also, to give a bit of background on Washoe County, as I mentioned, for those unfamiliar with it, you can see here in red, it is in the northwestern part of the state of Nevada. It is home to the city of Reno, which is perhaps more recognizable than the county name. And when it comes to heat in Washoe County, to give a little bit of context, between 2021 and 2025, there were between 7 and 16 days per year where temperatures reached or exceeded 100 degrees. It is also among the fastest warming places in the US, and that does apply specifically to the city of Reno. When it comes to wildfire smoke within that same period, there were 141 days impacted, and more than half of those days, 92, were in 2021 and 2022, which notably coincide with the two largest wildfire seasons. It is also county. It does tend to receive significant smoke transport from neighboring states. All right, to give a sense for the approach that we have taken to achieve that short-term goal of, or near-term goal of understanding the health impacts on households from exposure to compound events, we have 18 households and 26 participants across those households who are part of the project. And I will call attention up front to the fact that 18 households is not a large number, but this is a pilot project. It's an ongoing pilot project. So our intention here is not to come to very certain conclusions about things necessarily, but rather to explore topics, improve our understanding, and also to test and refine data collection instruments. Within those 18 households, there are 7 that have evaporative coolers, 7 that have evaporative coolers, 4 that have window ACs, 4 that have no form of cooling infrastructure, and 3 that have central ACs. And so the idea in diversifying household types within this small sample is to be able to understand how impacts may differ across cooling infrastructure types. The project has been running since 2004, so we've gone through 2 years of data collection and are entering a third this summer. And what we do is make 5 visits per year to each household to collect data, as well as 1 visit at the end of the first year of data collection to return that year's data to households in order to have a conversation with them about it and to get their initial reactions. And I'll be sharing some of those reactions in this presentation. So types of data that we collect during visits are indoor and outdoor environmental data, so temperature, humidity, particulate matter, and so on. Physical health data with a focus on heart and lung function, so blood pressure and EKG, pulse oximetry, spirometry. Mental health data using the perceived stress scale, or the PSS 14, which is a pretty simple and straightforward and commonly used stress test. And then during data collection visits, we also conduct interviews and surveys with households in order to understand their protective action decision making. And those surveys and interviews are informed by the protective action decision model. So as mentioned, this project has been running for 2 years already, and we're going into a third year of data collection. In the 2 years during which the project has been running, there haven't been large wildfire smoke events. So the project is essentially ongoing until we inevitably do have big wildfire smoke events and more significant compound events that will help us to understand health impacts and how they vary across household types. In the meantime, we do have some early insights into how households perceive risk related to compound events, how they mitigate exposure to compound events, and how increased localized knowledge of compound events may influence risk perception and exposure mitigation. And so that's what I'll be sharing here today. So when it comes to household perceptions of risk, extreme heat is perceived specifically to pose health risks for individuals with pre-existing conditions, so things like asthma or chronic venous insufficiency, and for children. Beyond that, it is perceived generally to cause discomfort, but not necessarily health risk. Extreme heat is also considered common. People just anticipate that summers are going to be hot, and as is the case in a lot of hot urban areas, heat here is also largely normalized. When it comes to perceptions of wildfire smoke, similarly, it is perceived specifically to pose health risks for individuals with pre-existing conditions. So again, things like asthma, or in this case, COPD, and for children. But different from heat, it is perceived generally to pose health risks to the population more broadly. It is also considered common, unfortunately, for Washoe County because the county does have just that much wildfire smoke. But unlike heat, it has not been normalized. So how those risk perceptions translate into household exposure mitigation decisions is that wildfire smoke exposure mitigation takes priority over extreme heat exposure mitigation. So with the exception of central AC households, when it is both hot and smoky, other households tend to do things like turn off the evaporative cooler if that's the cooling infrastructure that they happen to have. They close windows and doors and essentially do what they can to keep outdoor air from coming inside. But of course, in doing so, creating the potential for increased indoor temperatures. Despite the fact that wildfire smoke exposure mitigation is the priority, the reality for these households is that accessible wildfire smoke protective actions tend to be fewer in number in comparison to extreme heat protective actions. So when it comes to the types of things that are really going to make a difference for households, like weatherization, acquisition of different filtering technologies, they're often cost prohibitive. And so looking at the table here, where you have just a very quick summary of heat protective actions per household and wildfire smoke protective actions per household, and taking a quick glance, you can see that while across household types, people are doing an awful lot to protect themselves from both heat and wildfire smoke, the wildfires. So shifting from how people understand or kind of perceive heat and wildfire smoke broadly to how people have reacted to their household temperature and air quality information. Here in the upper right, you have a graphic showing indoor temperature distribution for combined visits 1 through 3 of year 2024, which are the 3 visits that were made during the summer and wildfire smoke season in 2024, during which there were compound events. But again, the wildfire smoke events were just not particularly long duration, and they weren't particularly severe. So we didn't see much influence from wildfire smoke in the data that we collected that year. And what you have here is information broken out by household type. So evaporative or swamp cooler, window AC, no AC, and central AC, and the percent of readings corresponding to different 10-degree temperature categories. And what you can see is that there's not a lot of variation across household types in this particular context of what would be a fairly normal summer, again, because it was hot, but not particularly smoky. And below you have the same information, but for outdoor temperatures. You can get a sense there. Doing things like closing windows and doors, turning off the evaporative coolers. And so we would anticipate seeing higher indoor temperatures. But it's also the case that most households have a thermostat or digital thermometer in their homes. And so they tend to be familiar with their indoor temperature values generally, meaning that even if this data had looked different, I'm not sure that it would have been of surprise to people. At the same time, 7 of 18 households expressed that they would like to increase their exposure mitigation when it comes to heat, but are largely financially unable to do so. Because at this point, and if you think back to that table that showed numbers of protective actions, people are already doing a lot, and most of these households have kind of reached the limits of what they can do financially. And so additional things that they would potentially do are kind of those big tasks like window replacement or acquiring central AC. It is important to note, though, that this expressed desire to increase exposure mitigation with respect to heat is based on known discomfort and known indoor temperatures. Again, not based on perception of risk. And then looking at household reactions to their indoor PM 2.5 data. So here you have similar graphics. The one on top shows indoor PM 2.5 distribution, again, across household types. And here you have the percent of readings in each AQI category of concern. And below you have the same information for outdoor PM 2.5. So you can see, especially in looking at the bottom graphic, the absence of influence of big wildfire smokes on air quality during that summer. And what is reflected in the indoor PM 2.5 percentages is really more indoor PM generation. So in showing this data to households, they were generally very surprised by their indoor PM 2.5 concentrations, especially in comparison comparison to the outdoor concentration. So it was actually quite shocking to people to learn that their indoor air quality could be lesser than outdoor air quality. It's the case that only one household has a digital PM monitor in their home, and so most people are unfamiliar with the fact that PM does concentrate within the home, and that there are household activities that they undertake probably quite regularly that do potentially generate indoor PM. What we've learned also is that there is a general notion that air quality is an outdoor issue and not an indoor issue. So there tends to be an assumption that indoor air quality is automatically good, hence people's strong reactions to learn that their indoor air quality was often in the category of moderate. 10 of 18 households expressed that they would like to increase their exposure mitigation, but again, are largely financially unable to do so. So again, these households have largely reached the limits of what they can do to protect themselves from heat and smoke, and remaining are those larger, less accessible options, in this case, acquisition of portable indoor air cleaners or central AC. But unlike the case related to wildfire smoke, as well as this household data. And while we don't want it to be the case that people react more strongly than they need to in learning that air quality can be moderate indoors, it was nonetheless pretty instructive to see how alarming that was to people. So then just to conclude with some tentative implications for household support, again, with household support being the long-term goal, education on heat health impacts may be needed to increase perception of extreme heat as posing health risks. And this is of particular importance given the prioritization of wildfire smoke exposure mitigation during compound events. So again, with the tendency of households to close up the house, turn off the evaporative cooler, close windows and doors, potentially allowing heat to accumulate, it does become all the more important that they are informed about risks associated with heat. Another is that increased availability of indoor air quality information may hold promise for motivating protective action. Again, going back to kind of the high and seeing what was only really moderate indoor air quality does suggest that they may similarly be surprised to see what their indoor air quality is during compound events. At the same time, there would probably be benefit in providing accompanying education on the relationship between air quality and health risks to help people or households be informed in thinking about how they might respond. Again, because we don't want to have people, reacting unnecessarily to what is normal fluctuation in indoor particulate matter. And then lastly, that households may already be employing high numbers of protective actions within available financial means. So other forms of support beyond things like education and information provision may be needed to further adaptation to compound events. And again, this is reflected in those high numbers of actions that these participating households are already taking, and the fact that they have essentially reached the means of what they can do. All right, thank you.
Thanks, Kristen, for that great presentation. We have time for one question. And the question is, how were the 18 households selected, and did they vary in socioeconomic status?
We recruited, DRI and an NPH teamed up on recruitment. So recruitment was open to households in select zip codes within the county. And we prioritize zip codes where households tend to be more resource scarce. And also parts of the county where we know that, say, when there are big wildfire smoke events, the smoke tends to concentrate and persist for a while. So there is some economic variation across households, but it is not particularly significant given the focus of this work on lower resource households.
Got it. Thank you very much.
Thank you.
And now we will turn back again to Mitchell Rogers. And I think we're looking good. See the presentation?
Yep. Can everyone hear me okay right now?
Yep, we can.
Fantastic. I apologize again for the inconvenience to folks, and thank you for hanging on tight with me. I'm going to leave my camera off just to be safe, but I promise I'm all dressed up for everyone and I'm giving you my best. So this afternoon, I'm going to be talking about the impacts of warming, humid summers on urban organic aerosol production and the field measurements that have been done to evaluate that. So to describe what all that means and kick off this discussion, I'm going to first start by going into showing actually my backdrop picture. And this is New York City on a hot, humid day in June of 2025. I'm sure many of you on the East Coast of the United States would be familiar with days like this. I only came to appreciate it when I moved here from California 4 years ago. But on days like this, in addition to being, muggy and generally unpleasant, the climate can actually lead to the production of air pollution, which you may see from the haze here. And this form of air pollution, like Kristen has actually mentioned before, is called fine particulate matter. And fine particulate matter, or PM2.5, are aerosols that are less than 2.5 micrometers in diameter, and collectively they're associated with millions of deaths per year globally. So this might lead to the question, where does PM2.5 come from? And to answer that, let's think about a mix of both anthropogenic or human, driven sources and biogenic sources, like cars, motor vehicles, power plants, trees, cooking, and they can emit both gases, but also particles. And the particles that are directly emitted into the atmosphere, we call those primary PM2.5. And this can be stuff like soot from your chimney or from cooking, or metals like in road dust, or primary organic aerosol, which was be emitted like from cooking or from traffic from motor vehicles. But also those gases that I mentioned earlier, these gases can actually react with other species in the atmosphere and oxidize and partition into aerosols to form secondary particulate matter. So that's particulate matter formed via the reaction of gas phase precursors. And this can include inorganic species like sulfate and nitrate, which you might have heard of, but also secondary organic aerosol. And we're going to focus on SOA, or secondary organic aerosol, and this gets a lot of community in the air, or a lot of attention in the air pollution research community for a couple of reasons. First of all, especially now, it's emerging as the most abundant component of PM2.5 in the United States, especially during the summer. This is summer PM2.5 composition in Queens, New York City, from measurements taken a few years ago. And if we see how this even evolves over time, from 2001 to 2009 to 2022, this is especially true in more recent years after emissions controls have reduced concentrations of inorganic species like sulfate and nitrate. Second, emerging evidence from epidemiological work, like that shown here, suggests that SOA has also carried outsized health effects and is even worse than total PM2.5 on a per mass basis. But lastly, since secondary organic aerosols formed in the atmosphere, it should make sense, or might make sense to some of you, that it's actually very dependent on climate. And this is actually a graph here that I have of two different kinds of organic aerosol. The gray is hydrocarbon-like organic aerosol, commonly associated with motor vehicles. That's pretty flat throughout the year. People are still driving, even if it's in winter. But this secondary organic aerosol, this is produced in the atmosphere. You can see just how dramatically temperature dependent it is, and how it is at much higher, twofold, threefold, fourfold concentrations in New York City. At higher summertime temperatures. So, more specifically, we've predicted that rising temperatures, and often shown too in measurements, that these rising temperatures will drive increased emissions of volatile organic compounds. These are the gas phase precursors to PM2.5, but also accelerate then the chemical processes themselves that produce secondary organic aerosol. And in the paper that I'm going to be focusing more on today, we're really focusing on the second question. And more specifically, you might be wondering, what secondary organic aerosol production pathways are climate sensitive? There's a lot of them. And to what extent can we actually control them? So the process that I'm going to hone in on today is aqueous phase production of secondary organic aerosol. And to describe what that is, I want to think about dry particles that, are formed in the atmosphere, have all those things that I just discussed earlier. Now, a lot of these components, like the organic aerosol and the sulfate and the nitrate, are hygroscopic. That means water loving. And these compounds lead to a lot of aerosol liquid water that will adsorb on and deliquesce, we say, into to form these kind of aqueous, mode particles. So we have an aqueous phase that will envelop and surround the particles, as you can see, and it will grow and increase at higher relative humidities. And second, then, water-soluble organic gases can then partition into this aqueous phase, or this aerosol liquid water, and then oxidize to make secondary organic aerosol. And I want to emphasize that this process requires that water phase. So this is only possible if we have that aqueous film or aqueous phase around the particles for these organic gases to partition onto. So we can get a net production of organic aerosol. So based on the steps that I've described, you might imagine that the steps of aqueous phase oxidation are sensitive to humidity for sure, but also heat. And we're going to talk about that for a bit. But before I do, to summarize, my introduction and kick off my motivation, secondary organic aerosol is a large fraction of fine particulate matter. It's highly sensitive to climate. We want to figure out more why. And specifically, that aqueous phase chemistry is suggested to contribute to an underestimated fraction of SOA and is an important part of SOA climate sensitivity. So to describe the methods, to evaluate the influence of aqueous phase chemistry on urban SOA, we made summertime measurements, with high time resolution of fine particulate matter in New York City. This was at one site in Queens, New York City. That's a part of the emerging NSF-funded Atmospheric Science and Chemistry Measurement Network, which I'm happy to talk about in the future. And then also, importantly, the AC4 NOAA-funded Aroma campaign. We had a ground site active on the roof of of the City College University of New York in Manhattan, New York. And at both sites, we had an aerosol chemical speciation monitor that's measuring the composition of PM2.5 every 10 minutes. And I'm going to talk about two objectives or two key accomplishments. First, we're going to quantify how aqueous phase chemistry accelerates SOA production. And then second, we evaluated how climate-driven positive feedback loops can then modulate this aqueous phase SOA production. And I'll note that this work that I'm doing has been made possible by the work of many collaborators and is published in Geophysical Research Letters. There's a QR code there below. So to get into this first point, I just want to say first that the aqueous phase production of secondary organic aerosol has really only recently been, predicted and modeled and observed, I would say most in the past 10, 15 years. And still finding evidence in general in any urban environment is important, as it's an understudied mechanism of SOA production. And to illustrate the framework of how we, found evidence of aqueous SOA production, I want to say that first, via just gas phase oxidation in the atmosphere, we would have production of both secondary organic aerosol, like I've talked about, but also ozone. So if there's, just traditional gas phase oxidation, these species will have a net production of both, and they'll be typically well correlated in an urban environment. But then if we look at how this slope of secondary organic aerosol to ozone changes with relative humidity and other chemical indicators, we can start to get evidence for this other mechanism, this aqueous phase oxidation and aqueous phase enhancement in secondary organic aerosol. So using these measurements, and if I just look at this across an entire summer in Queens, for instance, at high relative humidities, when we had enough aerosol liquid water, aqueous phase chemistry was driving an estimated 46% enhancement in secondary organic aerosol production in New York City. So this was a really important finding to us to show that a large fraction of the accelerated rate in secondary organic aerosol production is attributed to this aqueous phase mechanism that's dependent on particle composition and climate. But then, we found evidence of this mechanism, sure, but how does the environment and how do climate-driven positive feedback loops modulate this production? So to show this graph and spend a bit of time on it, there's a few variables going on. We have temperature on the x-axis and relative humidity on the y-axis. And as we increase in temperature and relative humidity, we're seeing a combined increase in secondary organic aerosol, but also these dots get bigger, and that means we're also having more secondary inorganic aerosol like sulfate, nitrate, and ammonium. And what this is evidence of is a couple of things. It's really evidence of these positive feedback loops where at higher temperatures, we can have more oxidation, more production of things like sulfate and secondary organic aerosol, and that these species are very hygroscopic. They love water. So when we up that relative humidity, we're going to get more aerosol liquid water inside the particles. And that then provides the phase for the production of more secondary organic aerosol and more sulfate, that otherwise wouldn't be possible. But then, best of all, those secondary or inorganic species also enable more reactions and even a reactive uptake of organic species like isoprene epoxidiols that are oxidation products of isoprene, monoterpenes emitted from trees to produce secondary organic aerosol. So, I hope this gets across then that temperature and relative humidity can kick off and accelerate, the production of additional secondary inorganic and organic aerosols. And the last point that I will spend some time on is that you might have noticed that an important ingredient, I'll go back one slide, an important ingredient in this process are these secondary inorganic aerosols. So sulfate and ammonium and nitrate. And we can actually look at where the air masses were coming from in New York City to better illustrate how these different variables impact aqueous phase secondary organic aerosol production. So if we look at air masses coming from the southeast here, along the northeastern corridor, along the I-95, there's lots of major cities here in the northeast megalopolis. There's DC and all these cities around New Jersey, Philadelphia, major cities, lots of freeways, lots of cars, lots of nitrate production from NOx, right? We also have elevated sulfate production from power plants and elevated ammonium. And, with all of that, we then have the ingredients to have more aerosol liquid water and more production of sulfate. That's this sulfur oxidation ratio. So this is highest for these air masses that were traveling along the Northeast corridor compared to cleaner conditions in upstate New York. And that from all that, we're having, the highest amount of this secondary organic aerosol, the fraction that's from aqueous phase production, especially, highest from this C1 cluster that travels along the Northeast corridor, where we have the nitrate, the sulfate, and the higher relative humidity from being along the coast. We have all these variables that will lead to an increased production of secondary organic aerosol. So to summarize then some takeaways, using summertime measurements from 2 sites in New York City, we evaluated the influence of aqueous phase chemistry on urban SOA. We found that aqueous phase chemistry during these high relative humidity episodes that I showed earlier drives a 46% enhancement in SOA production, and that this is likely the result of positive feedback loops between aerosol liquid water and secondary inorganic species and secondary organic aerosol, but it's propelled forward by high relative humidity and also, importantly, high temperature in the summers. And most importantly then, or with great policy interest, despite steep declines in nitrate and sulfate, because these species are so hygroscopic and they can enable the reactive uptake of organic gases, these species still have an outsized influence on secondary organic aerosol production via this aqueous phase mechanism, so that future controls for nitrate and sulfate can matter a lot. So to close, I want to really acknowledge all the members of the Gentner Research Group and my advisor, Professor Drew Gentner, as well as all the collaborators at Aerodyne Research and Jose Jimenez's research group, and our funding sources, NSF, NOAA, and NYSERDA, as well as our additional campaign partnerships and collaborators. So I'll leave this slide up with some takeaways and take any questions. Thank you.
Thanks, Mitchell. We are at the top of the hour, but we did want to get one question in. How quickly do these transformations occur in the atmosphere, and are there specific spatial hotspots within the urban landscape where these reactions are most active?
Yeah, that's a great question. Thank you. I'll go to this slide first, just because it was my next extra slide for some background. On the timescales, it can be very rapid. It can be on the order of hours, especially in hazy conditions. You can get rapid production of sulfate within hours. But generally, I would say within the order of hours to a day. And these aerosols can be in the atmosphere for over a week. So that's kind of the timescales of this. So in other words, the emissions, of cities far upwind can influence the concentrations and production of aqueous phase secondary organic aerosol. And as far as hotspots go, generally that kind of will lead to the conclusion that areas that are near or downwind of or within places that emit lots of NOx and SO2 and have high nitrate and sulfate concentrations, but also importantly, that high relative humidity to have more liquid water and high temperature. Those are going to be expected hotspots. So that's what makes the Northeast corridor, an important spot. Another important spot that's been well studied is the Southeast U.S. A lot of work has been done in Atlanta, as you can imagine, lots of precursors there to make these products. So thank you.
Thanks, Mitchell. I'm going to turn it back over to Lauren to close us out.
Thanks again for everyone who joined us today, and really appreciate and want to thank our great speakers, Ronnie, Mitchell, and Kristen, for your presentations. We will be posting a recording of this webinar on the NOAA Climate Program Office website within the next few days, so feel free to take a look at that if you want to rewatch anything or look back at any of the slides. And then once again, I'll just flag that registration is open for our webinar on May 21st, which will be focused on urban heat research and solutions. So you can scan the QR code or visit our website to register for that. And with that, we will go ahead and conclude for today, but thank you again to everyone and see you next time.